Hello there everyone, welcome to Physics 11 at 11. What we're doing today is taking a look at graphs and graphing and just reminding ourselves about certain things that have to be there, certain calculations that can be done in order to create a good looking document, in order to create a good looking presentation and communicate well. So let's go through the top, fill in the spaces along the way, and then you'll have the opportunity to do some real type of questions afterwards. So, going from the top, we got graphing rules, labeling the axes. On the graph, you have the x and y axis. The x-axis is usually the independent variable, just like you heard in science class back in the day. The y-axis is the dependent variable. So usually you choose values for the independent axis. You choose values for the x-axis. And then the results you get from the experiment depend on those values. So those are along the y. Also included when you label your axes, you have to have the units present, because that will help the reader see what's being measured and the units that are there. Second part is give the graph. It says AN, but I think we can just think about it like this instead. Give the graph a meaningful title. Okay, because the graph is about communicating something to the reader. So make sure that the title actually communicates something. These next couple of blanks, these are more for if you're doing it on paper, which you are free to do. You are also free to use technology such as Desmos and whatever else you have available. So this might not apply if you're working with technology. Often it's chosen for you once you enter the points. But regardless, here we go. If we're doing the paper version, what you are recommended to do is use the entire page. Because what this does is it creates a nice big graph. It's easy to read, and your reader will enjoy that. Second of all, you choose a scale that's easy to use. Sometimes with the numbers, they can be a little bit awkward, and you have to find 0.3 of a square or something like that. So a trick to do is just make the scale bigger so that the weird numbers can fit in nicely. All right, so look after yourselves and make a scale that's easy to use, that matches the data points that you have. Now, once you've gone through the hard work of acquiring the data points, you have to put them on the graph, much like you see here on the left already. Hey, the example's been started for you. Now, it says if they look like a straight line. Okay, and that's if you squint your eyes. Because I think if you look at this, these points here, yeah, these ones are pretty obviously a straight line. But if you do an experiment and you're not sure, give your eyes a squint, and if it looks more or less like a straight line, then treat it as one. And so to fill in the next couple of blanks, it says plot your data points. If they look kind of like a straight line, draw a line of best fit. Now, if you're using technology, this can be done for you. Okay, but if you're using paper, then you draw it in there, as best as you can, just using your eyeballs to see that it goes close to the points that are there. In a perfect world, having some of the points, an equal number above and an equal number below the lines, plus passing through some points along the way. It's kind of subjective, but if you're not using technology, so do your best there. And to help you do your best is the last blank, using a ruler. Okay, the line's going to be inaccurate, so at least making a straight line will help it make it easy to read. Now, the goal, as we're going to see in a later section, the goal is often to get the equation for a straight line, because that describes the relationship between the independent and dependent variables. And then once you have the equation, well, you can count yourself as successful. I guess because in the back of my mind, this equation's pretty famous. The guy that figured it out, is going to be remembered for a long time. Right. So that's one of the things we're going for. Try to figure out the equation. So what you do is you choose 2 points that are 1, easy to read, going through a corner if possible. And I've got a couple circled there that I considered not bad. So easy to read, on the line. Okay, you're not choosing your original data points. What we're doing is the data points are there. We're going to put the line on, and then we're going to use the line as the description for the data. Okay, so when you're choosing 2 points, make sure they are on the line and not your original results there. The last step, last blank, it says, as something as possible, far apart. Because that just helps you get an accurate reading for the slope. But as I said, we're doing it by hand, so do the best that you can. So what I've shown so far are things that need to be on the graph: title, units, labels, and then how to select points. Well, what we're going to do, finding the slope is one typical calculation for a line, and it's super important actually. So we're going to remind ourselves how to find the slope of a line joining 2 points. So that's going to go back in time to like grade 10. Formulas like this: y2 minus y1, these are the y coordinates, over x2 minus x1. And you use the 2 points that you selected, and those are the ones that I got there. So substituting them in. Oh, I guess I could show you this. We have 2, 6, and we have 9 and 26. So no real order. You can switch these around if you want. x1, y1 goes in the first point, x2, y2. If you want to reverse those and have this point is x2 and y2 and that is x1 and y1, you can. It won't matter. Okay, but importantly, these fit together. x1 with y1, x is first, x2, y2. Right, again, x is first. Okay, substitute carefully, and we can get the slope for this line that we have here. So, yeah, I see it's a 20. I took it as a 26. If you got better eyes than I, you might want to. You could say, oh, it's a little bit more, but taking it as 26. The other one's 6, and yeah, same sort of thing. Maybe a decimal of some sort, but I don't know what the decimal is, so I'm just going to round it to 6 there. This is how it goes when you're doing it by hand. Then you got a 9 for x2, just as it says. And then a 2 for x1 like that. So doing the subtractions, you just get 20 over 7, which is some sort of a decimal. Now, what we found is now the slope of a line, which allows us to put the value for the slope in for m, since this is the general equation, or a form of a line, y-intercept actually. So to get the line, we got to find the slope and the y-intercept, which is what we did, or at least we got the slope. So we can improve our equation now by doing this. 7x plus b. Now to finish it up, we got to figure out what b is going to be. So what you do is when you're working with y-intercept line like this, you select a point on the line, put it in for x and y, and then the only thing left will be b. So that gives you the y-intercept. So a point that I'm going to use, and I think it's accurate, is this point here, 7 and 20.5. And the only reason I chose it, and I'm doing this by hand, and I see a 7 on the bottom, so it'd be nice if x was 7. So I took a look at the graph and said, yeah, okay, 7's a good x value, and the y value, pretty easy to read. Looks like a half, so I took it as this. So all I'm going to do now is put the 7 in for x, 20.5 in for y, and then solve for b. So the line which you have in front of you, I'm just doing it again, x plus b. That's the slope. Brackets just to show it's being substituted. And then, yeah, no brackets, just because there's a number on its own there. And we have plus b left over. So what happens with the 7s? Gone. We get 20.5 is equal to 20 plus b. And so solving for b, you get 0.5. And so by finding this y-intercept, this last point, we can now get the equation for our line of best fit. And that will be, well, you can write it down before me, line of best fit. That will be that y is equal to 20 over 7, the slope that we found there, times x, and then plus 0.5. Now, tempting to give one of these and sign it off as finished, but there's actually another thing that we can do. And that is the last thing here. Replace y and x with variables or names that are more descriptive. Just don't leave it as x and y. Put the variables in that fit the experiment or the equation. Okay. Now, I see there's 3 blanks here that I just got into the equation. I like that better. But let's fill in the blanks here. Finding the equation of your line. It says we usually write the equations in the form of, and I snuck it in there, but officially y equals mx plus b, where m is what? M is the slope. And b is what? B is the y-intercept. I'll tuck it over here for now. The y-intercept. says intercept. Okay, so we have to replace the variables x and y with something more descriptive. Well, if we go take a look at the graph, there wasn't anything there. So it's up to us to put a title, because that's missing. There are numbers there, but to put a variable on this side along with the units, right here as well, along with the units, and then improve the equation. So a cute thing I saw was people swimming with coffee. So we'll say coffee swims. Coffee and swim speed. And so here, if you remember, it went up to 25. And this is what makes it cute, because 25 meters per second is about 90 kilometers an hour. That's a lot of coffee. All right, so along the bottom, of course, we'd have cups, where the units would be, I guess just C for cups, eh? However much one cup is. Anyways, we got our numbers down here, and I think it went up to about 10 or something like that. So, to improve the equation, we can just put more meaningful variables in there. Speed of the swimmer is 20/7 times C for the number of cups that they drink plus 0.5. And this would be a good looking equation for the graph that we had. Okay, so I hope you found that useful, informative. Please follow these steps when creating the graphs and doing the calculations for lines with your work. And in doing so, you'll have a